Welcome friends, this is my second video on the topic differentiation. In the last video, we discussed the meaning of derivatives. In this video, we shall first of all revise the derivatives of some standard functions which we have studied in 11th standard, and also we shall revise some rules of differentiation which are also studied in 11th standard. And after that, we shall see a new rule of differentiation which is the rule for differentiation of a composite function. And after that, we shall solve some examples on that new rule also, which is also called chain rule, that is included in 12th standard syllabus. So at first, the revision on the rules of differentiation and standard derivatives. As you can see, the list of derivatives, these are the derivatives which we have seen in 11th standard. The first list here, you can see in the first table there are a few functions, and in the second table also there are a few functions. At first, you can see the first function, it is c constant, means you can take fx is equal to c, means fx is equal to 2, fx is equal to 5, fx is equal to 2 by 3. These are all constants. Their derivative is 0. The logic behind it, you can easily understand this, that constant means which is something which is not changing, and if is a function or a function is a constant, then it is not changing. That means there is no rate of change there. That means the derivative of a constant is 0, because derivative means rate of change, and rate of change is 0 because originally function is constant. So constant derivative is 0, you can remember it. The second list, you can see the type of these examples is this, x raised to n. X raised to n type of function whose derivative is nx raised to n minus 1. You can put different values of n, any real number you can put here, and you will find nx raised to n minus 1 as the derivative of that function. Starting with a simple example like x cube, n is written as 3 here. If n is 3, then n is 3 and n is 3, so 3 minus 1 2. So the answer for a derivative of x raised to 3 is 3x raised to 3 minus 1, that is 2. If you consider another example, x means x raised to just 1. So 1 is not mentioned, but it means it. So x means x raised to 1, is derivative as per this formula will be 1 x raised to 1 minus 1, that is 1 x raised to 0, that is 1 into 1, which is 1. Better you can remember this directly, derivative of x is 1. Similarly, derivative of x raised to minus 3 is given by this formula as minus 3 x raised to minus 3 minus 1, which is minus 4. So in this manner you can find derivative of x raised to minus 3, which is 1 upon x cube, if you want to write it in that manner. 1 upon x cube means x raised to minus 3, derivative is minus 3 x raised to minus 4, coming from this formula, which can be rearranged as minus 3 into 1 upon x raised to 4, which can be written even as 1 minus 3. It can be written as minus 3 upon x raised to 4, written in the denominator as x raised to minus 4, written in the denominator as x raised to 4. So you can write that this way as well. 1 upon x. Now 1 upon x is actually x raised to minus 1. Now it looks like this x raised to n. Now its derivative is found as 1 minus 1 into x raised to minus 1 minus 1. That is minus 1 into x raised to minus 2, which is simplified as minus 1 upon x raised to 2. So derivative of 1 upon x should be directly remembered as minus 1 upon x square. Derivative of 1 upon x should be directly remembered as minus 1 upon x square. Similarly, derivative of root of x. Now root of x looks like x raised to n if you write it as x raised to half. Root of x means x raised to half. Now it looks like this formula, this form, and then its derivative will be found by that same formula. It comes out as 1 upon 2 root x. Actually it is initially written as 1 upon 2 as per this formula, x raised to 1 upon 2 minus 1, which is minus 1 upon 2. And if you rearrange this 1 upon 2 as it is, x raised to minus half, written in the denominator as x raised to half, and x raised to half means root of x. So directly you can remember this derivative of root of x. So whenever it's the question of finding derivative of root of x, you can directly tell it is 1 upon 2 root x. That way we can see the examples of this type, and I have shown some examples like this: x cube x, x raised to minus 3, 1 upon x, root of x, which are applicable in this section. The second, you can see the group of examples here. These are called exponential functions. A raised to x. A raised to x, its derivative written here is a raised to x log a. Now you can write anything in place of a which is positive real number and which is not 1. So a can be written as 3, 2, 0.5, 0.1, anything, but not 1 and not 0 and not negative number. So you can have any number like 0 point something 1 or something, then not 1, and then finally you can go on taking any number after that. So I have chosen 3 raised to x. Its derivative as per this formula is 3 raised to x log 3. Even you can have 2 raised to x, 0.5 raised to x. 0.5 raised to x will be 0.5 raised to x into log 0.5. Or you can have 5 raised to x, derivative will be 5 raised to x log 5. So that way we can write the derivative. Now what is this? E raised to x. Its derivative is also written in this form as e raised to x log e. But log e, actually it should have been log e written here, but log e is 1, and therefore it is not mentioned. So you can write e raised to x as e raised to x. Like I said, I repeat, e raised to x its derivative is e raised to x log e, but log e is 1 because when we don't write any base, it means that it is e. So log e to the base e is 1, so not mentioned here. It's 1. So e raised to x derivative is e raised to x log e, but log e being 1, it's simply e raised to x. 3 raised to x derivative is written there. Now let's turn to this part. This is the logarithmic functions group. Log x to the base a in general, its derivative written here, and this can be used in these examples. So starting with suppose log of x to the base a, the rule itself tells us that the derivative is 1 upon x log a. So a, once again in the same manner, a can be taken equal to any positive real number which is not 1. So I can choose 10 here, for example. Then it should be 1 upon x log 10, because the rule is log of x derivative, log of x to the base a's derivative is 1 upon x log a. So 1 upon x, log of x to the base 10's derivative will be 1 upon x log 10. Now what about this? Log of x only, not base is not mentioned. And like I told earlier, whenever log with without base is mentioned here, without base is given, we understand that base to be e. In mathematics theory, we normally consider as natural logarithm simply written as log of x. That means we don't use don't write e, but it is understood to be e. The base is understood to be e. If it is e, then what would you write there? You understand that this is e, it will be log of e real. Log of e means 1, so therefore it is not mentioned. So base e is normally not mentioned, it is understood to be e, and then as per this formula it should be 1 upon x log e being 1. So we simply remember derivative of log of x as 1 upon x. Then we have already discussed this. Then the last part here, you can see there are 6 functions which are trigonometric functions. These trigonometric functions, for the convenience of the students, I shall read those. Sin x, cos x, tan x, cot x, sec x, cosec x. Their derivatives respectively are, see, sin x derivative is cos x, derivative of cos x is minus sin x, derivative of tan x is sec square x, derivative of cot x is minus cosec square x, derivative of sec x is sec x into tan x, and derivative of cosec x is minus cosec x into cot x. You have to remember these derivatives which you have studied in 11th standard. This whole list is there with you in 11th standard book, textbook, and even you must have studied them, but it's required to be repeatedly read, and these derivatives should be prepared very well. They should be ready with you. So you can draw this table and write these derivatives for your convenience so that you can solve the examples easily. Let us revise the rules of differentiation which you have studied in 11th standard. The first rule, you can see there are 2 rules written in one statement, plus sign and then minus sign. Here also there is plus sign and minus sign. Read one sign at a time. Suppose I read it as with positive sign. How do I read it? If y is equal to u plus v, then dy by dx is equal to du by dx plus dv by dx. Again, if you read it as y is equal to u minus v, then dy by dx is equal to du by dx minus dv by dx. These rules in short are called as sum rule and difference rule of differentiation. Third rule is actually written as 2 because 2 rules are here written in one line. So I shall call it as second rule. Y is equal to u into v, then dy by dx is equal to u into dv by dx plus v into du by dx. Read it carefully, you are knowing this, but remember that properly. It's the product of two functions. Suppose you consider u as first and v as second function. Then the derivative is taken as first function as it is u, then derivative of the second function plus second function v as it is, and then into derivative of first function. So this is the third rule. Then the fourth rule is if y is equal to u upon v, means the quotient rule. It is called product rule. This is called sum rule, difference rule, product rule, and then this is the quotient rule. In this quotient rule, you have y is equal to u upon v, means division of the two functions is given. Then the differentiation is done as dy by dx is equal to v into du by dx, second function, and this is first function. Suppose then second into derivative first minus first y u into derivative second dv by dx, and whole divided by then second function square. We shall try to see some simple examples to understand these rules. Starting with the first example, suppose y is equal to x cube plus sine x. Then that fits in the first rule, u plus v. U is x cube and v is sine x. So differentiation will give me dy by dx is equal to d by dx of u. Du by dx means d by dx of u. U is x cube. X cube is derivative. D by dx of x cube plus d by dx of v. V means in this case it is sine x. So if you solve this, you will find it equal to d by dx of x cube. D by dx of x cube is 3x square. So it will be 3x square. As per the rule x raised to m, you can find this derivative as 3x square plus d by dx of sine x. D by dx of sine x means derivative of sine x is cos x. That's it. So in this manner we can find the derivative of the functions which are added together to give another function, and in this case we use the rule of differentiation which is called sum rule. Then we can see some more examples of other rules also. Let us see the example on difference rule. See, y is equal to x square minus 2 raised to x. It looks like u minus v. Y is equal to u minus v. Then the derivative of y as per that rule is derivative of u minus derivative of v. That means derivative of y is dy by dx, which is written equal to derivative means d by dx of u is x square in this example, minus d by dx of v means 2 raised to x. That if you simplify d by dx of x square, it looks like x raised to n. So the first formula, you can remember that nx raised to n minus 1 gives us derivative of x square as just 2x. You should remember them. Then minus d by dx of derivative of 2 raised to x. Now this 2 raised to x is different from x square. 2 raised to x fits in a raised to x form. Now its derivative of a raised to x is a raised to x log a. So derivative of 2 raised to x is 2 raised to x log 2. 2 raised to x log 2. So this is how we can find the derivative of difference. Then we can think about derivative of product. Let us take another example. Derivative of product. So suppose I have y is equal to x into sine x. X into sine x. Now this is looking like u into v. Y is equal to u into v. Y is equal to u means x into sin x means v. So u into v. So how do you apply this rule? Here you have dy by dx. Differentiation will give you dy by dx is equal to x means u means x into d by dx of v means d by dx of sin x plus v means sin x into d by dx of u means x. Now just have to find out the derivative of sin x and derivative of x. This sin x and this x will be repeated in the next step. So x repeated, then d by dx of sin x, you know, is cos x, and plus sin x as it is into d by dx of x. You should remember that d by dx of x is 1. And if you finally write it in the nice form, x cos x plus sin x. So dy by dx in this example, where we had y is equal to x sin x, is found like this. Dy by dx is x cos x plus sin x. Now let us see one example on quotient rule. Suppose y is equal to e raised to x upon tan x. E raised to x upon tan x. So clearly it is u upon v form. Quotient rule has to be used. Your u is e raised to x and v is tan x. So let us find derivative of y dy by dx is equal to, how do you write this rule? How do you use this rule? It's written as v. V means second function. It's u is e raised to x and v is tan x. So v means tan x into d by dx of u. du by dx means d by dx of u. du by dx means d by dx of u. d by dx of u is your e raised to x. So it's d by dx of u means e raised to x in this case, minus u means e raised to x, and into d by dx of v in this case is v is tan x, and then whole divided by tan x whole square means tan square x. We can write in the next step. This is written as, now you just have to solve these two things, d by dx of e raised to x and d by dx of tan x. If you know these two derivatives, you can write them easily and then the answer will be over. So tan x into d by dx of e raised to x, derivative of e raised to x is simply e raised to x. E raised to x is a special function. E raised to x is a very special function. Its derivative is e raised to x itself. So you can easily remember that. D by dx of e raised to x is e raised to x minus e raised to x as it is. Then d by dx of tan x is sec square x, and whole divided by tan x whole square means tan square x. This is the answer. You can, for simplification purpose, you can take this e raised to x common and write this as, if you want, you can write this as e raised to x into e raised to x taken common from the two terms, tan x minus sec square x whole divided by tan square x. That will be enough. This is not so important. Just using the rule and writing the derivatives properly is important. So this is how you can find dy by dx if y is e raised to x upon tan x, or any other example with this form. So far we discussed the standard derivatives, and also we discussed 4 rules of differentiation which are studied in 11th standard. Now you can see some examples whose derivatives can be easily told. X square, for example, 5 raised to x. These derivatives are known to you. Just in mind you can go through these derivatives. Derivative of x square, 2x. Derivative of 5 raised to x, 5 raised to x log 5. Derivative of e raised to x is e raised to x itself. X square, like I said, derivative is 2x. Sin x, derivative is cos x. Derivative of tan x is sec square x. Now it's time to see this set. On this side you have a table where there are some functions there, like log of x whole square, 5 raised to sin x, e raised to tan x. What about their derivatives? Now earlier we found these derivatives very easily using our knowledge of 11th standard, but these derivatives cannot be found on the basis of your knowledge of 11th standard. So for these derivatives, I need to know one rule called rule for derivative of composite function or chain rule. So we shall study that rule now. So before going for any discussion on composite functions derivatives rule, that means rule for derivative of composite function, we shall try to understand what is a composite function. There are a few examples already written here. These are all composite functions, and therefore we are not able to find their derivatives on the basis of your 11th standard knowledge. First, look at this log of x whole square. Log of x whole square is a function of log of x, and log of x then is a function of x. On this side, if you see, x square is a function of x only. X square is a function of x. Log of x whole square looks like x square, but it is not a function of x directly. Similarly, phi raised to x is a function of x. Phi raised to x is a function of x. But phi raised to sin x depends on, first of all, sin x, and sin x then depends on x. So phi raised to sin x is a function of sin x, and sin x then is a function of x. So these functions are functions of functions. Phi raised to sin x is a function of another function sin x, and sin x is a function of x. E raised to tan x is a function of another function tan x, and tan x then is a function of x. Similarly, you can think about the remaining two, sine of log x and tan of root x. What about tan of root x? Tan of root x is a function of not directly x, it is a function of root x, and root x then is a function of x. Therefore, these functions are functions of functions, and functions of functions are called composite functions, and their derivative is found by the rule of derivative for composite functions, or it is called chain rule. So let us see that chain rule now, so that we can find the derivatives of these kind of examples. So let us see the chain rule or rule for derivative of composite functions in details. The statement of the rule is shown here. Theorem states the rule here. How do you read this? If y is a differentiable function of u, y is equal to f of u is a differentiable function of u. That means y is a differentiable function of u, and then you can see y is a differential function of u. Y means f of u is differential function of u. Then you are stating that u is a differentiable function of x. U is equal to gx is a differentiable function of x. So u is a differential function of x. So again see this, y is a differentiable function of u, and u is a differentiable function of x, then y is a differentiable function of x. What are you saying? Y is a differentiable function of u, and u is a differentiable function of x, then y is a differentiable function of x, and its derivative dy by dx is written as dy by du into du by dx. So rule is dy by dx is equal to dy by du into du by dx. So in short, you can remember this design. Y is the differential function of u, and u is the differential function of x. Then you can't find directly dy by dx, because what you can find is dy by du, because y is the differential function of u, so you can find dy by du. Similarly, u is the differential function of x, therefore you can find du by dx. So you can find these two derivatives, multiply them, and as per this rule, this product is dy by dx. This product itself is dy by dx. We just saw the statement of chain rule, which is written in short like this. If y is a differential function of u and u is a differential function of x, then y is a differential function of x, and dy by dx is dy by du into du by dx. So let us prove this rule, and for the proof we have to make some initial steps. You have to remember them, because in the exam this proof can be asked. So let us write the proof. Let delta x be a small increment in x. Let delta x be a small increment in a small increment itself means very small thing. So if you have a small change in x, increment you can understand as small change. So if you make a small change delta x in x, that means delta x in x, on x what depends is u and y depends on u. So it's a chain, y depends on u depends on x. If you make a small change delta x in x, there will be a small change or whatever change, but there will be a change in u. Due to this change in u, there will be a change in y. So let us denote these corresponding changes by delta u and delta y. Let delta u and delta y be the corresponding increments in u and y respectively. So let us see what we have written here. Let delta x be a small change in x. Due to that small change or small increment in x, there is a small increment delta u in u. Due to this increment delta u in u, there is an increment delta y in y. That's what we have written. So if you take the first delta x increment very small, then delta u will also be small and delta y will also be very small. We shall use this argument later in this proof. We can write this step delta y by delta x is equal to delta y by delta u into delta u by delta x. So this is balanced. Delta y by delta x, delta y by delta u if you balance out, it will be just delta y by delta x. So delta y by delta x can be easily written as delta y by delta u into delta u by delta x. For our convenience we have written this. Now what we'll do, we shall take a limiting condition, take limit delta x tending to 0 on both sides. Take limit delta x tending to 0 on both sides. So what will happen is this, limit delta y by delta x as delta x tending to 0. I have taken a limit delta x tending to 0 on the left side. Same thing I will do on the right side. Limit delta x tending to 0 on the right side. Right side is delta y by delta x, delta y by delta u into delta u by delta x. This limiting condition is applied on both sides. Delta x tending to 0. Now we shall use the laws of limits and write this limit delta by delta u into delta u by delta x as separate limits will be written, and we can write this as, I shall wipe this out and write it in the next segment. So we had written delta y by delta x as delta y by delta u into delta u by delta x earlier. Then we took limit delta x tending to 0 on both sides. Now I shall separate the limits on the right hand side. So what I'll write is this limit delta x tending to 0 of delta y by delta u into limit delta x tending to 0 as of delta u by delta x. So in this step we have separated the two limits. Then this limit delta x tending to 0 can be replaced by delta y tending to 0 or delta u tending to 0 if I want it. And for that our argument, if you remember, it is y depends on u and u depends on x. So if there is a small change delta x in x, there is a change delta u in u, there is a change delta y in y. So if you take delta x very small, delta u will also be very small, delta y therefore will be very small. So if delta x tending to 0 is a condition you take, then correspondingly delta u will also tend to 0 and delta y will also tend to 0, because they depend, delta u and delta y depend on delta x. So that argument we can make, and we can write here, we will write as delta x tends to 0, therefore delta u tends to 0. Even delta y also tends to 0, because delta x tends to 0, delta u tends to 0 and delta u tends to 0, therefore delta y will also tend to 0, but we shall not use that. So we shall not write it. So coming back to this step again, now I will write this as limit delta y by delta x as delta x tending to 0 is limit delta y by delta u. I will make the change here, delta x tending to 0 will be replaced by delta u tends to 0, remember this, into no change here, limit delta u by delta x as delta x tends to 0. So I have not made any change in this part. Here I have made this change. Just note that change. Note that change. Delta x tends to 0 is replaced by delta u tending to 0, because we can do this. Then we shall make another argument using the statement. Now statement says that y is the differentiable function of u and u is the differential function of x. It means that dy by du exists and du by dx exists. So we shall make use of this information. So far, by making a change here, delta x tending to 0 replaced by delta u tending to 0, I have got this step. Now we shall make use of y being differential function of u and u being differential function of x. Before that, I will give number 1 to this statement. I shall leave it for a while, and let's use this information as y is a differentiable function of u and u is a differentiable function of x. What I can write is dy by du can be written, y is a differential function of u, that means derivative of y with respect to u exists. Derivative of y with respect to u means dy by du, that exists, and if that exists, we write it as limit delta y by delta u as delta u tends to 0. Similarly, in the second line we have written u is the differential function of x. That means I can write du, see, y, u is the differential function of x, that means I can find out du by dx, and du by dx exists, and if it exists, we write it as limit delta u by delta x as delta x tending to 0. This is standard formulae of derivatives. So we can write dy by du and du by dx like this. These I will consider as number 2. These statements or these steps can be used in this step. So I can replace this limit delta by delta u as delta u tends to 0 by dy by du, and limit delta u by delta x as delta x tends to 0 by du by dx. So what will happen in 1, therefore from 1 and 2 I can write limit delta y by delta x as delta x tends to 0 equal to, how can I write this? This can be written as dy by du multiplied by this limit delta u by delta x as delta x tends to 0 is du by dx. So what we have is limit delta by delta x as delta x tends to 0 is equal to dy by du into du by dx. Now looking at the statement, we have said that y is the differential function of u, that means dy by du exists. Similarly, u is a differential function of x, so du by dx exists. And two things, if they exist, their product will also exist. Therefore, this whole right side will exist. If this whole right side exists, that means whole left side exists. And if left side exists, what would you call this? Limit delta y by delta x as delta x tends to 0 exists means dy by dx exists. This is nothing but dy by dx. So we can finish this in few lines after this. So let us take this as 3. From 2 and 3 we can say, see, from 3 itself we can say that the RHS of 3 exists, because you know that dy by du exists and du by dx exists, so RHS of 3 exists. Therefore LHS of 3 must exist. LHS of 3 must exist. That means limit, what is LHS of 3? Limit delta y by delta x as delta x tends to 0 exists. And if it exists, we write it equal to dy by dx. So in short, limit delta by delta x as delta x tends to 0, which is dy by dx, exists. So from 1 and this last step, we can write in 1, this was your LHS. So we can write this LHS as dy by dx is equal to, earlier we had written in 2 as dy by du into du by dx. So from 1 and even 2 and 3. So you make the changes, make the use of these statements and write dy by du is equal to dy by dx is equal to dy by du into du by dx. So hence the proof. You can read the whole proof in the textbook, it is given. Even you can consider this proof, discussion on this proof in step-by-step manner. We can understand the steps very easily, but in this discussion we have made use of this limited space, therefore we had to wipe it out very often. But you can write this proof properly in the notebook, and then you'll understand the actual way of writing it. But you can understand it using this discussion. So let us see the examples and some corollaries based on this composite functions derivatives rule in the next video.